Let us consider the mathematical model describing fall of a body to the earth. We begin with the differential equation of the second order. Equation 1, describing the free fall of a body with a constant mass m, which is not equal to 0, under the Earth's gravitation g, neglecting the friction in Earth's atmosphere. Here x is a function of t, time t, and x dot is the derivative of x of t, and g, as I told, is the acceleration of gravity. The general solution to equation 1 is obtained by integrating it twice. Namely, we write equation 1 in the form dx dot dt equals minus g integrated minus g integral dt, and obtain x dot equals minus g times t plus c1, where c1 is an arbitrary constant. Equation 2 gives the following expression for the velocity: v equals x dot. So from 2 we have v equals minus g times t plus c1. Equation 3. Now we integrate equation 2. We write it in the form dx dt equals minus gt plus c1. Integrate this equation and obtain x equals minus g integral t dt plus c1 integral dt, whence x equals to minus g over t over 2 times t square plus c1 times t plus c2, where c2 is another arbitrary constant. By letting t equals to 0 in our equations 3 and 4, and denoting v at t equals to 0 equals v0, x at t equals to 0 equals x0, we obtain the physical meaning of the integration constants c1, c2, namely c1 equals v0 and c2 equals x0. Therefore, the trajectory and the velocity of the body in the free fall are written as follows: x equals x0 plus t times v0 and minus g over 2 times t square, and v equals v0 minus g times t. Equation 6. Now we consider the conservation laws and energy of the falling body, a free fall of a body. We solve the equations 3 and 4 with respect to the constants c1 and c2 and obtain the following equations: x dot plus gt equals C1, and x minus t x dot minus g over 2 t square equals C2. Equation 7. Note that the conservation laws, these are conservation laws, equation 7, because C1 and C2 are constants. So these conservation laws contain the time t. We eliminate time t from the conservation law 7 and introduce the new constant c equals half of c1 squared. This gives just calculations, plus g times c2, and obtain the following conservation law that does not involve the time explicitly. 1/2 times v squared plus g times x equals c. Conservation law 8. Multiplying both sides of equation 8 by the mass m and denoting the constant m times c by a constant E, we arrive at the conservation of energy E, which is defined by E equals to m over 2 v squared plus mg times x. The conservation of energy E is known from school to everybody. So the conservation of energy 9 can be written in terms of, because it is constant for any time, so we can take that time equals to 0 and then obtain m over 2 v squared plus mg x. So, and if time is 0, then it becomes m over 2 v0 squared plus mg x0. So we can use either the form 9 or the form which is written right now. Now we turn to conservation of body when we take into account Earth's atmosphere. Several approximations for considering Earth's atmosphere. One of them is that the atmosphere adds the term which is linear with respect to the velocity. Namely, we have the following model. Instead of free fall, we now consider the following. Gamma m x dot plus mg equals to 0. The equation 10. So the difference from the equation for the free fall is that now we have the additional term gamma times m times x dot, and we have to solve this equation, and we would like to compare with the solution of the free fall. In equation 10, gamma is a positive constant different from 0. Now we have to integrate equation 10, which is linear second order ordinary differential equation, which is non-homogeneous because of the last term plus m times g. Therefore, we have to find one particular solution of the non-homogeneous equation and reduce the problem to the homogeneous equation. In order to find that particular solution, we know that equation 10 contains the term with x dot and does not contain the term with x without dot. Therefore, it should have a particular solution which is linear in time t. So we look for that solution in the form a times t, where a is a just unknown constant. Substitute it in equation 10 and obtain that a equals minus g divided by gamma. Therefore, the particular solution of equation 10 is the following. X equals minus g divided by gamma times t. 11. Now we look for the general solution of the homogeneous equation m x double dot plus gamma m x dot equals to 0. We, as it is known from just the first course on differential equations, that we can use the Euler substitution and look for the solution in the form x equals exponent of alpha times t. X equals exponent alpha times t. So substituting this expression into equation, a homogeneous equation, we obtain the following. Lambda times lambda plus gamma equals to 0, whence we have lambda 1 of roots equals to minus gamma, and another one, lambda 2, equals 0. Therefore, we have the following two particular solutions to the homogeneous equation. x1 equals exponent minus gamma t, and x2 equals 1. Therefore, the general solution to our equation, we take the linear combination of x1 and x2 and add the particular solution which we obtained above. We obtain the general solution to equation 10. So this is x equals c2 minus g over 2 times t minus c1 exponent minus gamma t. Equation 12. From here we immediately obtain, by differentiating, the velocity, the expression for the velocity. V equals minus g over gamma plus gamma c1 exponent minus gamma t. And now we have the solution, general solution of equation given by equation 12, and expression for the velocity given by equation 13. From these two equations we can again find C2 and C1, which will be conservation laws. And therefore we would like to consider the conservation law, which is again as above, which does not depend on t, because C1 and C2 will depend on t, so we'll exclude t. Let's go to that expression. So after solving equations 12 and 13 with respect to C1 and C2, and introducing new constants, C1 tilde defined by gamma square times C1 and C2 tilde, which equals gamma C2 minus G over gamma, we obtain the following conservation laws. C1 tilde equals, we obtain the following: gamma times V plus G multiplied by exponent of gamma t, and this equals to C1 tilde, and V plus gamma x plus gt equals C2. So we have two conservation laws for t, but they contain time t in a very quite complicated form. So now we eliminate t from these equations, which is because two equations for t. We obtain the following conservation law, which is free from time t, namely gamma times v plus g multiplied by exponent in the power minus, and in the brackets, gamma divided by g times v minus gamma square over g times x equals c, equation 15. So this is our conservation law. Here we denoted by introduce new constant c equals c1 tilde exponent minus gamma over g c2. Quite complicated expression for c, but it comes from calculations which we don't put here. So we have now the following results. A trajectory of the falling body in the Earth's atmosphere is given by equation x equals c2 minus g over gamma t minus c1 exponent minus gamma t, and this was equation 12. And the velocity v equals minus g over gamma plus gamma times c1 exponent minus gamma t, equation 13. And the conservation law, gamma times velocity v plus constant g exponent to the power minus gamma over g times v and minus gamma square over g times x equals c, equation 15. And now we can again express the constants of all constants c1 and c2 in terms of the initial conditions. In order to do that, we again let t equals to 0 in equations 12 and 13, and using the notations which were given by equation 5 above, and obtain that x0, this is from equation 12, x0 equals c2 minus c1, and equation 13 gives v0 gives gamma c1 minus g over gamma. Solving these equations for c1 and c2, we obtain c1 equals v0 over gamma plus g over gamma square, and c2 equals x0 plus v0 over gamma and plus g over gamma square. And using these expressions c1 and c2 in equations 12 and 13, we write equations 12 and 13 for trajectory and the velocity in the following forms. X equals x0 plus v0 over gamma plus g over gamma square minus g over t and minus V0 over gamma plus G over gamma square times exponent minus gamma T. And V equals minus G over gamma plus V0 plus G over gamma multiplied by exponent minus gamma T. So quite complicated expressions for the trajectory x and for the velocity v compared to the case of the free fall. Therefore, in order to compare these expressions with the similar expressions for free fall, we make an approximation when gamma is a small parameter and expand the expressions for x and v into Taylor series, and we obtain the following expressions. X approximately equals x0, just compare with the above equations, plus tv0 minus 1/2 gt square plus gamma over 6 times gt cube minus 3v0 t square plus small term with respect to gamma, O small of gamma, and v equals approximately equals v0 minus gt plus gamma over 2 times gt square minus 2v0t plus again O small of gamma. O small of gamma means that this term contains at least the gamma square. When gamma tends to 0, the equations, let's denote them by 16. These equations, equations 16 coincide with equation 6 for the free fall. Now what is important for us is we have to compare the conservation law for the fall in the Earth's atmosphere with the free fall. For that we write the conservation law 15 for the fall in the Earth's atmosphere. Let's remind that equation again. It's gamma times v plus g, and here exponent minus gamma over g v minus gamma square over g times x, and this was equal to constant c. Now we have to compare this conservation law with the conservation of energy for the free fall, and again to do that we expand the exponent into Taylor series and obtain gamma v plus g multiplied by 1 minus gamma v over g minus gamma square x over g plus 1/2 gamma square v square over g square plus gamma cubed x times v over g square minus 1/6 gamma cubed v cubed over g cubed plus and higher order terms in gamma equals to constant. We will keep here only the terms of the order gamma cubed, and obtain the following approximate conservation law. G minus gamma square times 1 over 2G V square plus X plus 1 over 3G square times, what I put in the bracket here, gamma cube V cube equals, approximately equals to C, equation 17. Okay. Since in equation 17 G is constant, we can move the term with this term G to the right hand side of equation 17, multiply the resulting equation by the constant factor minus G over gamma square, and arrive at the following form of the approximate conservation law 17. 1/2 V square plus Gx minus gamma over 3GV cubed approximately equals constant. This is approximate conservation law for the fall of a body in Earth's atmosphere. You see that the difference of the conservation law from the energy E of the free fall, which was equal to 1 over 2 V square plus Gx, is proportional to gamma V cubed. So it means that falling body due to the friction of the Earth's atmosphere gives us that the energy, the part of the energy equal to gamma, which is proportional to gamma V cube, gamma times V cube, goes for heating the body. That's why we see that the rockets, for example, falling to the Earth, they are burning like meteorites also. The heating because of the Earth's atmosphere. So this is the result what we had after solving mathematical models. Of course, in reality, the approximation which was given in our case is one of approximations. There are many other approximations, but we consider just one in order to understand how it works. So thank you.